Hello everyone. Today we're gonna learn about divide and conquer algorithm. The first documentation about divide and conquer algorithm dated back as far as the 1950s. So you can see it's a quite old algorithm, but yet still very popular these days. This is not a too powerful algorithm, but it's gonna help us to understand more about recursion and for loops. This tutorial is a part of the data structures and algorithms class. First, we're gonna talk about a typical problem solved by divide and conquer algorithm. And our problem today is a very popular problem, that is sorting an array of numbers. The way divide and conquer solve problem is, it's gonna divide the original problem into two or more easier to solve subproblems. And then when the subproblems are easy, we're gonna conquer them. That means we're gonna solve easy subproblems, then combine the subproblem solutions to create our final solution for the original problem. Let's have a look at our problem, sorting an array of numbers. This is a very popular problem and probably one of the oldest problem in computer science. And the way divide and conquer solves this problem is, it's gonna divide this array into smaller subarrays. For example, in this step, it cut the array from two halves. And it's gonna keep dividing subarray into halves, like this one, until we find that the problem is easy to solve. So in this case, we keep dividing the array into halves, until we can no longer divide them. That's when the subarray becomes single element arrays. So why do we choose to divide the original array into single element arrays? Why not 2 elements arrays or 3 elements arrays? Well, we can divide as small or as big as we want. But in this case, single element arrays work best for us. Why? Because single element array itself is a sorted array. So just by dividing the problem into smaller subproblems of single arrays, we can skip the step of solving easy subproblems. Because the single element array is already sorted by itself. It's important to know that this solve step needs to be done to find a solution for easy subproblems. But in our case, here, we don't need it, because single element array is sorted by itself. So dividing the original array into single element arrays is a clever way to solve easy subproblems. Next, we're gonna combine the subproblem solutions to create our final solution. And that is merging the sorted subarrays. So combining single element sorted array of 15 and 26, gonna give us 15 and 26. Combining single element sorted array 13 and 7, gonna give us 7 and 13. And then we're gonna combine the 2 elements sorted arrays of 15, 26 and 7, 13. And that's gonna give us 7, 13, 15 and 26. And with the same combination logic, we're gonna continue for the other half of the original array. And then we have a sorted array of 2, 3, 5, 7, 13, 15, 22, and 26. So that's how divide and conquer works. We divide the original problem into smaller easy to solve subproblems. Then we solve easy to solve subproblems. And then we combine subproblem solution into final solution. That's how we divide and conquer. Next, let's have a look at the recursion implementation of sorting an array with divide and conquer. Again, our problem is sorting an array of numbers from small to big. And this is our divide and conquer solution. First, we have our base case. And we're gonna use our base case to decide how small we want to divide our problem to. And in our case, we're gonna divide the original array into single element arrays. That's where array length equal to 1 here. So our base case is used to control how small we want to divide the problem into. Then we have the divide step. We're gonna have the left array, half of the original array, and the right array is the other half of the original array. Now we're gonna call merge sort recursively in these subarrays, so we can keep dividing until it hit the base case. And by applying what we have learned before about recursion, whenever we see a recursive call in a calculation like this, we immediately know it's bottom-up processing. That means all the cases gonna stack up and wait for the input of the base case. So what we do when we see the code look like this is we're gonna draw out the recursion tree like this one that we have here. And then we're gonna go to the base case, where we have single element subarrays, and calculate from there. So in our case, we're gonna have our first base case of the division of 15, and then the second base case of 26. So when we have the base cases here, next we're gonna think about solving easy subproblems. In our case here, we don't have to do the solve step, because the single element array is already sorted by itself. But if you use divide and conquer to solve other problems, remember that you might need to do this step. After solving easy subproblems, meaning having sorted arrays, we're gonna combine subproblem solution into the final solutions. And that is combining the sorted left array and sorted right array. We're gonna write a combine function separately down here. And after combining, we're gonna return our result. Here we're gonna print out the left sorted array, right sorted array, and merged sorted subarray in every of our iterations. And if we run our divide and conquer algorithm, this is our result. From the original unsorted array, we have our sorted array. But let's have a look at our recursion steps here. We read our code, we see a recursive call into a calculation, we draw out our recursion tree, and we immediately go to the base cases. So that's what we have here in our first iteration. We have 15 and we have 26. And they are here, our base cases, from bottom up. Then we merge the left and right array, and we have the sorted array of 15 and 26. Then our recursion is gonna go into another pair of base cases, which are 13 and 7, which is this branch that we see here. And that's what we have here in our next iteration. We have 13, we have 7, and then when we combine them, we have 7 and 13. After that, when we have sorted subarrays of 15, 26, and 7, 13, we're gonna combine them. And it's gonna give us 7, 13, 15, and 26. And that's what we have here in our iteration. We have 15, 26, we have 7, 13, and after merging them, we have 7, 13, 15, and 26. And divide and conquer gonna keep doing so for the right subarray. That's when we're gonna have 2, 3, 5, and 22, which is what we have here. And at our final combination, we merge the two sorted subarray from left and right. Then we have our final solution of 2, 3, 5, 7, 13, 15, 22, and 26. So that's how divide and conquer works with a recursion implementation. Now there's an important information that we want to note here. You may have noticed there's a lot of number and subarray are in gray color. And this is intentional. That is, even we draw out the tree and it looks like this, the order of execution is not parallel. In fact, it started with the leftmost base case, which is 15. And that's what we see here. And then with the next leftmost base case, which is 26. That's what we see here. So this gray color, less visible subarrays here, is to remind you that even with recursion, we only looking at one data point at a time. For example, for this one, we only looking at 15. And after having 15 on the left, 15 gonna wait for another data point on the right, which is 26. And when we have data from the left and the right, we're gonna do the combination step, which gonna give us the sorted array of 15 and 26. So again, with even recursion and the tree draw out like this, we can see that the actual execution is from data point after data point. And the sequence of which data point gonna be processed next gonna be decided by the call stack. Next, we're gonna briefly talk about the combination step. So what we do is we use two indexes, one for the left array and one for the right array. And then we compare the numbers of the indexes to decide which one's gonna go to the merge array first. Then if the left array has some element left, we're gonna push them all into the final merge array. And we're gonna do the same thing in the right array. Then we return the merge sorted array. And the time complexity of our divide and conquer implementation is O n log n. And the space complexity is O(n), with n is the number of the element in the array. Next, let's have a look at our for loop implementation of sorting an array. This is also called an iterative implementation. Now we know that for every recursion implementation, we're gonna have the equivalent for loop implementation. And either for recursion or for loop, although they are different in approach and names, they eventually do the same thing. That is, processing data point after data point. And we know that for our recursion implementation of divide and conquer, we have the time complexity of O n log n. This is gonna give us some hint. for our for loop implementation. By this time complexity, we know this implementation must give us the capability to look at all the data points one by one, that's the ON part, and to look at the data point again, but dropping half of the data points left after each iteration. That is the O log n part. For that, we're gonna have a for loop and a binary search. It can be binary search nested in for loop, or it can be the other way around, which is for loop nested in a binary search. With this kind of logical thinking, we can have a possible solution of sorting an array like this. We're gonna have our original array and a sorted array, and we're gonna initialize the sorted array with the first element of the original array. Then we're gonna run a for loop in the original array to go through all the elements. So in this case, we have 26. And we're gonna use binary search on this sorted array to look for the index of where we can insert 26. And in this case, when we do a binary search for the sorted array, we know that 26 is bigger than all elements in the array. So the insert index is 1, and we insert 26 after 15. Then we're gonna continue with our for loop, and we get to 13. And we do a binary search on the sorted array with 13 to see where should we insert 13. And we can see that 13 is smaller than all the elements in the sorted array, so the insert index is 0. And we insert 13 before 15 and 26. And we're gonna keep doing so for the rest of the number of the original array. For example, for the last one we have 22. And we're gonna do a binary search for index to insert 22. And we know that 22 is bigger than 15 and smaller than 26. So the insert index is 6. And that is where we insert 22. After that, we can return our result as a sorted array. And for this method, we have a binary search nested in a for loop. So our time complexity is gonna be ON log n. Next, let's have a look at our implementation for sorting the array of numbers from small to big using for loop, the iterative approach. First, we initialize the sorted array with the first element of the original array, like we see here. Then we run a for loop to go through all the elements. And we're gonna use the current element of the array to compare. For our binary search, we initialize the left pointer, the right pointer, and the index to insert the new element. Then we calculate our middle index. When middle index converges with left and right index, we're gonna compare our element array I with the element at the middle index to decide the index to insert our new element array I. And then we break out the loop. Otherwise, we continue on the left or on the right based on the element of the middle index and the value of the current element array I. After having the index to insert, we insert the element into the sorted array. Now there are two edge cases that we need to solve here. The first edge case is when left index equal to 1, middle index equal to 2, and right index equal to 3. And the loop runs forever. We examine the case and we know that the index to insert is mid plus 1, and then we break the loop. The second edge case is when left equal to 0, mid and right equal to 1. For this one, the loop exits before we have the index to insert. And we know the index to insert is right plus 1. After handling our edge cases and print out some key information, we can return the sorted array. And if we run this algorithm with the same input that we have at recursion, we have the same result of the sorted array. That is 2, 3, 5, 7, 13, 15, 22, and 26. Now let's have a look at some of the steps. First, we have a sorted array of 15. Then we're looking at 26. And we run a binary search. We found the index to insert 26 only after 15. Then we continue with 13. And we run a binary search for 15 and 26. Then we found the index to insert is 0. And we insert 13 before 15 and 26. And as we keep doing so, our final sorted array result is what we want. We have two more example inputs here to see how our algorithm handle the edge cases. You can uncomment these cases and have a look by yourself. Next, we're gonna generalize the characteristic of problems that can be solved by divide and conquer. We can try divide and conquer with any problem type, as long as our inputs pass the split test. And the test is if we split the input into halves, it doesn't change anything at all. For example, our sorting number problem passes the split test. That means sorting this array, or just half of this array, like 15, 26, 13, and 7, are actually the same. Or even you have a longer array than this one. The problem characteristics are the same. and the input data for divide and conquer algorithm are usually array, string, or graph. Then if we try divide and conquer, then we know that the time complexity is gonna be O n log n. Now the fastest way to try divide and conquer with any problem is that you need to remember this picture and these steps. And when we have some inputs, you're just gonna plug it in here and try to divide, try to solve, and try to combine to see if it gives you a solution. Sometimes it does, sometimes it doesn't. But the key thing here, if you remember it this way, you can quickly think if divide and conquer can give you a solution. So remember this framework, divide, solve, and combine, and apply it with a problem that passes the split test to see if you can have a solution. And if the reasoner give you a solution, you can just plug in your logic in these blocks to use divide and conquer. The first block, you use exit condition, base cases, to control how small you want to divide. The second block, you divide, and remember this is bottom-up solution, so you're gonna use the base cases to solve your subproblem, which is the next block, solving the subproblem starting from the base cases. And then the next block is combine. You're gonna combine the subproblem solution to create the final solution, and then you return the result. For an iterative approach, or a for loop solution of divide and conquer, you can remember this picture here, that we have a for loop and a binary search nested in the for loop, because it's gonna give it a time complexity of O n log n. And then you're gonna have the structure of your solution look like this. A binary search inside a for loop, or it can be a for loop inside a binary search. Next, to summarize, we can try divide and conquer with any problem type, as long as the input passes the split test, and the input can be array, string, or graph. Then we can try to divide, solve, and combine if it gives us a possible solution. And if it does, the time complexity is gonna be O n log n. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.